Today we have Dr. Xiang Ren. She recently defended her PhD at the University of Toronto, and she'll be joining the Curry College of Computer Science at Northeastern University as an assistant professor in September of this year. She is genuinely interested in computer system software and has taken a multi-pronged approach to improving system performance by building automated tools that help developers debug performance issues and carrying out comprehensive performance studies and designing performance systems. Her research artifacts have been adopted or requested by industry and the academic community. So thank you, Dr. Ren. The floor is yours.
So performance makes or breaks a piece of software. Internet Explorer was infamously plagued by slow performance and was eventually retired. Severe performance issues can lead to failures and costly outages. A major AWS outage actually started with performance issues in the networking devices. On the other end of the scale, even small performance degradation can be costly. Google finds that a 0.5-second delay in page load time has caused a 20% drop in repeat traffic. Yet despite its importance, there are many obstacles to building performance systems. Software systems today are complex and evolve rapidly. For example, Meta's largest service gets thousands of code commits every day. The rapid rate of software evolution can pose challenges to maintaining good performance. The goal of my work is to improve the performance of system software. My approach is to understand the factors that prevent developers from building performance systems and build tools that help developers automate manually difficult tasks in maintaining good performance. More broadly, my PhD work falls into two directions: on improving system performance and on building automated debugging tools. In this talk, I will first introduce my work on studying the performance evolution of Linux, and my second piece of work on automating performance root cause diagnosis using relational debugging. Linux is the most popular OS kernel for servers, smartphones, and embedded systems. Now, Linux's code base is growing rapidly. Every week, around 1,000 commits are added to the Linux kernel as shown in the commit graph. Given the code base is growing so fast, is the Linux kernel actually getting slower or faster? Existing studies on Linux performance do not answer this question. They focus on scalability or specific parts of the Linux kernel, like the scheduler. So in order to answer this question, we decided to study the performance evolution of Linux. First, we designed an updated benchmark called LE-bench to reflect the kernel usage patterns of real workloads. LE-bench tests basic kernel functions like page fault, context switch, thread process creation, as well as several I/O system calls and networking system calls. LE-bench has been adopted considerably in the academic community and used by a number of papers, and it has been used by developers at Amazon. We ran LE-bench on 41 Linux versions spanning 7.5 years and collected latency data for every version. Surprisingly, the performance of these core operations have fluctuated significantly in the past. In addition, their performance are actually getting much slower in newer versions. In this 3D graph, the x-axis on the bottom has different Linux kernel versions, and the y-axis on the right shows different LE-bench tests. And we use version 4.0 as the baseline because it is the fastest on average. You can see that compared to version 4.0, some operations are nearly 100% slower in newer versions. After careful analysis, We found a total of 11 root causes that account for most of the performance changes. The bottom graph highlights the versions each root cause is present, and the top graph is a subset of the performance trend. You can probably notice some of the correlations between the slowdowns and the root causes. The 11 root causes further fall under 3 categories. 4 are security enhancements, 4 are new features, and 3 are misconfigurations. In fact, the need to accommodate an increasing number of security enhancements caused most of the recent slowdowns in the kernel. These security enhancements include patches for Meltdown and Spectre v2. Misconfiguration is a second most significant contributor of slowdown. And finally, other forms of slowdown are caused by the overhead of adding new features. We found that by disabling all the root causes, we can speed up Redis benchmark workloads by 56%, Apache by 33%, and Nginx by 34%. We further break down these performance penalties and found that besides fundamental performance trade-offs required to increase security or introduce new features, there are extra costs paid for the lack of testing, optimization, or careful configuration. In fact, 3 misconfigurations are plain mistakes that do not benefit any type of workload. Unfortunately, they weren't always caught and fixed on time, or the correct configuration is not backported to versions still supported, and cause widespread slowdown in kernel operations. One of the misconfigurations mistakenly turned on a debugging feature called forced context tracking, which slowed down kernel operations across the board because it adds overhead to every kernel entry and exit. But it remained enabled for 11 months, during which it became a well-known performance issue. In addition to misconfigurations that do not benefit any workload, we found new features were not always introduced with optimal performance. One of the new features is called C-group memory controller. This feature supports containers. The feature was introduced with considerable overhead, but only underwent a significant optimization 6 years after the initial release. And what's more, we were actually able to find ways to optimize away some of the performance degradation. For example, for 2 of the security enhancements, we created simple patches that can avoid most of their overhead without decreasing security. In addition to finding ways to remove the overhead of security enhancements, we also found that 2 features were intended as optimizations for only specific workloads, and reconfiguring them speed up our tests as well as macro benchmarks. The fact that we were able to find low-hanging fruits to improve kernel performance provides a window into the challenges associated with maintaining good performance for a complex and rapidly growing system like Linux. In fact, with frequent kernel releases, performance tuning is so time-consuming that distribution and kernel developers simply do not attempt it. To give you a bit more idea about the performance tuning process, this is how I used to analyze the performance changes in Linux. First, I notice an increase in the latency of a test. What I'll do next is to profile the slowdown using a profiler like perf. In this case, the highest ranked do more work function is clearly a hotspot. So I read the source code to understand why do more work was executed. And I found that it executed because of a configuration change, which I conclude is the root cause. Now this is a super contrived example. In reality, most of my time spent in the Linux study was spent in the diagnosis process. As a result, I became interested to automate performance diagnosis. Inspired by the experience and findings from the Linux performance study, my next piece of work proposes relational debugging, which can automatically pinpoint the root causes of software performance issues down to specific lines of code. Relational debugging is inspired by the observation that existing root cause diagnosis techniques are designed for functional failures. However, performance issues tend to be quite different from functional failures. For example, functional failures tend to have clear-cut absolute outcomes where we know the bug is triggered as long as certain errors occurred. And existing techniques operate on top of this assumption. Consider statistical debugging, for example. It works by identifying predicates that are highly correlated with the failure. For example, if every time the server crashes, a flag is set to true, and when the same flag is set to false, the server never crashes, statistical debugging will return the flag being set to true as the root cause. The very design of statistical debugging requires inputting many execution variants explicitly labeled as fail or success. However, performance issues tend to have outcomes that must be determined in relation to input workload size. This fundamentally breaks the design of statistical debugging. For example, say we have a program that is consuming lots of memory. The program could be experiencing severe memory leaks, or it could be that the program is simply processing a large number of requests, so consuming more memory is normal. Existing root cause diagnosis techniques look for simple signals of a bug, like an error or a crash, and do not consider the input workload size. So they would consider the two executions as having the same outcome. To summarize, existing root cause diagnosis techniques, including statistical debugging, delta debugging, and Kyrax, are designed for functional bugs with clear-cut absolute outcome. So they cannot be generalized to diagnose performance issues, and they especially do not work on some of the hardest performance issues for human developers. Now back to the example, while both the faulty and healthy execution consume the same amount of memory, if we look at it at the request level, it is obvious that one of them is consuming memory excessively. The insight is that when it comes to diagnosing performance issues, it is important to find the right reference point within an execution for comparison. To illustrate this idea further, I like to use an analogy between performance and relative motion in the physical world. For example, an observer finds a person running at the speed of 5 kilometers per hour. The next day, the observer spots the same person on top of the train, but they appear to be moving at 35 kilometers per hour. Did the runner turn into Usain Bolt? Now the stationary person is confused, but if we move the reference point to the train, however, we'll find that the runner is still running at the same speed. In this case, the speed of the runner observed by the stationary person is like the overall memory consumption. The train speed is like the request rate, and the runner speed is like the amount of memory consumed per request. Just like the observer has a hard time directly determining the runner's true speed, in complex software systems, it's hard to capture the root cause of performance issues without examining relative performance at the right reference point. Inspired by this insight, our solution to automating the root cause diagnosis of performance issues is to cater to the relativeness of performance. we created a novel technique called relational debugging, which identifies the right reference point within executions for comparison. Relational debugging is generalizable to different software performance issues and can pinpoint the root causes of some of the hardest performance issues down to specific lines of code. Now, implementing relational debugging in complex real-world systems can be challenging. This is because there is a huge number of instructions that can serve as reference points. How can relational debugging efficiently find the right reference point that captures the root cause? To reduce the search space, relational debugging first ensures that each reference point can both affect the performance and can observe a change in performance. Otherwise, the reference point is not useful. By carrying out these two checks, relational debugging is able to filter out a large number of irrelevant reference points. And further, an important idea that guides the design of relational debugging is that it divides the execution up and examines performance between fine-grained execution events. Doing so effectively eliminate reference points that don't capture the root cause. To illustrate how relational debugging works, I'm going to use the example from before, where two executions consume the same amount of memory, but the first one executed 100,000 requests, and the second one only executed 1,000 requests, and is having severe memory leaks. In this case, the symptom is memory usage. We map it to concrete program operations that directly affect memory usage, which in this case are malloc, which allocates memory, and reclaim, which reclaims memory. Now we translate the problem into explaining the number of times malloc and reclaim occurred in each execution. Relational debugging takes as inputs both the symptoms, which are malloc and reclaim, and a reproduction of the good and bad runs and their binaries. And the rest of the analysis is completely automated. Let's focus on reclaim for now. What the analysis does next is to perform a combination of static and dynamic program slicing, which finds instructions that affect the execution of the symptom reclaim through control flow and data flow dependencies. This slide shows a program dependency graph obtained from this process, which is simplified to only contain function calls. In this diagram, the main function handles requests in the loop. Each request may trigger garbage collection or GC, and eventually garbage collection reclaims memory by evoking reclaim. In the main function, the request function, and the GC function are causal predecessors of reclaim because they need to occur before reclaim can happen. So I've added a new function here called garbage collection, or GC. What it does is that it automatically reclaims memory that is no longer in use. Back to the program dependency graph. Relational debugging operates on top of this graph. It starts from the most general reference point, which is the main function in this case, and gradually moves towards the symptom at reclaim to zero in on the most specific root cause. I'm going to express this algorithm in terms of pseudocode. In this snippet, S stands for the performance symptom, which is reclaimed in the left-hand side, and P stands for a predecessor of the symptom. Starting from the predecessor farthest away, which is the main function in the graph, relational debugging iterates towards the symptom. At every predecessor, it tests whether it can move the reference point to the next predecessor, or should consider the current one as the root cause. To start, we observe the symptom which is reclaimed from the perspective of the main function. Using the example from before, in the first execution, the main function eventually executed reclaim 100 million times, but the second execution only executed reclaim 1,000 times. We represent each of these two numbers with a new representation called a relation. This relation represents each time the main function executed the number of reclaims that happened as a result. More generally, a relation between a reference event and a target event is the number of target events that are causally related to each reference event. In the previous example, the main function serves as a reference event, and the reclaim function is the target event. So back to the example, the relation did change between the executions. In other words, from the perspective of the main function, we can observe a difference in the number of reclaims executed. But intuitively, the main function doesn't quite capture the root cause, and we should be able to move the reference point closer to reclaim. But how can we realize this in an algorithm? This piece of pseudocode represents how we check whether we can move the reference point from one predecessor to the next. Here, P stands for the current predecessor, and P prime stands for the target of the move. Essentially, if the relation between P and P prime has not changed between the two executions, we can carry out the move. So in order to check if we can move the reference point from the main function to the request function, relational debugging zooms in to examine the execution between main and request. And from the point of view of the main function, we find that request was executed 100,000 times in the first execution, but only 1,000 times in the second execution. Now, because relational debugging finds that the relation between main and request has changed, it concludes that it cannot move the reference point from main to request. However, we haven't exhausted all the options yet. According to the pseudocode from before, if we cannot move a reference point, we must consider it a root cause. But actually, relational debugging carries out additional checks when it cannot move a reference point. What it does is to further explain the changing relation across the two executions between the current predecessor P and the target of the move P prime. If there are further causes found, relational debugging carries out the analysis on the cause as a new symptom. Only when the change in the relation cannot be explained further does relational debugging declare the current predecessor as a root cause. So back to the example, relational debugging tries to explain why the number of requests executed by main changed between the executions. And it finds that request is an input to the program, and this changing relation is driven by a changing input. What this tells us is that if we observe reclaim from the point of view of main, there is actually a hidden variable of the number of requests. So the main function is really not a good reference point, and relational debugging moves the reference point to the request function. Now, relational debugging further examines the symptom reclaim from the point of view of each request. In these two sets, each number represents the number of times a request invoked reclaim. Remember in the previous case, the relation is just one number. If the reference event occurred multiple times, then for each occurrence of the reference event, we actually obtain a data point of how many causally related target events are executed. And the relation becomes a set of numbers. Back to the example, we can further represent each set with a distribution. Clearly, the two distributions have shifted significantly. In the second execution, each request invoked reclaim much less often. However, relational debugging still wants to find a more specific root cause. In particular, it wants to figure out if it can move the reference point to the GC function. To do this, relational debugging zooms in to look at the execution between request and garbage collection, or GC. It temporarily treats the garbage collection function, or GC, as a symptom and observes GC from the point of view of each request. So, from the point of view of each request, we find that the probability it triggers garbage collection is still the same in both executions. Let's say it's both at 10%. In this case, because the relation between request and GC did not change across the two executions, relational debugging concludes that it can move the reference point from request to GC. Intuitively, the root cause cannot possibly lie within request logic because the execution between request and GC has not changed from the perspective of reclaim. As a result, we consider GC an equivalent reference point to request, which means that they both can capture the same root cause. So we keep the more specific reference points of the two, which is GC. This helps us narrow down the root cause of the memory leak to logic inside the garbage collection function. Now, relational debugging doesn't stop here. It keeps iterating until it finds a specific root cause in the GC logic. Actually, the previous example illustrates how relational debugging captures the root cause of Go 909, a real bug that causes severe memory leaks, where the user finds that the program executes normally with the 64-bit go runtime, but consumes excessive memory with a 32-bit go runtime. Go 909 impacted many workloads and was extensively discussed. But diagnosing Go 909 was nearly impossible. More than a year after the initial report, the root cause was only discovered through trial and error. But why was Go 909 so hard to diagnose? It's because it doesn't have an absolute root cause. In fact, the GC algorithm failed to reclaim objects in both the good and bad ROM, but the root cause occurred more often in the bad ROM. So there is no obvious exceptional events in the bad ROM that can serve as obvious clues to the root cause. Actually, this property of Go 909 also breaks the assumptions of existing techniques because they are limited to identifying root causes in the form of absolute execution differences, where the root cause occurs in the bad ROM but not in the good ROM. They cannot diagnose the root cause of Go 909. Relational debugging is able to precisely capture the root cause of Go 909. Before I go into the details, I'd like to firstly quickly explain the root cause. Let's look at these two objects. The first one is a reachable object that is reached by the pointer p returned by malloc, which allocated the object. The second object is an invalid object with no real pointers pointing to it. However, its address happens to be the same as the value stored in the constant Q. The job of a garbage collector, or GC, is to automatically reclaim objects that are no longer reachable by any pointers. For example, after scanning the stack and heap, GC finds the first object is still reachable by a pointer and marks the object to prevent it from being reclaimed. A precise GC algorithm should know Q is not a pointer and reclaim the second object. However, this GC algorithm will mark the second object, preventing it from getting reclaimed. In fact, the root cause of Go 909 is that most of the objects marked by GC are invalid objects in the 32-bit execution. The memory leak is significantly worse in the 32-bit execution, where the difference in memory layout causes constant values to collide with object addresses more often. Relational debugging is able to precisely capture the root cause of Go 909. It automatically identifies mark as a reference event and malloc as a target event. Recall that marking an object signals that the object should not be reclaimed. In the good run, most of the mark events mark reachable objects. We know these objects are reachable because their pointers are valid and have a data flow dependency on malloc, which we can automatically identify through program analysis. In the bad run, most of the mark events marked invalid objects, whose fake pointers are constants that do not depend on malloc. Relational debugging represents the root cause using a relation, which describes the number of malloc events that each mark event depends on. In the good run, most of the mark events mark reachable objects, which depend on malloc, so the set is mostly populated with ones. In the bad run, most of the mark events mark invalid objects that do not depend on malloc, so the set is mostly populated with zeros. Representing each relation with its average, we find that only 1% of the mark events in the bad run marked reachable objects, and the rest of the mark events mistakenly marked invalid objects, causing a severe memory leak. Finally, a subtle point you might have noticed is that this relation captures, given an event that happened later, how many predecessor events it depends on. We call this type of relation a backward relation. Conceptually, a backward relation captures, given the same unit of output, is it still produced by the same unit of input? The other type of relation is a forward relation. A forward relation captures, given an earlier event, how many successor events does it lead to? Relational debugging builds both types of relations. This is because the two relations are not equivalent of each other, but rather complement each other to capture different types of root causes. In the case of Go 909, the forward relation actually does not capture the root cause, as it represents the distribution of valid objects' lifetimes, which does not change significantly between the execution. On the other hand, the backward relation represents the number of objects marked that are actually valid, which does experience significant decrease in the bad run and captures the root cause. In addition to Go 909, we applied relational debugging on 11 more complex real-world bugs. And relational debugging is able to diagnose 10 of the 12 bugs. For one case, the bug is in the OS kernel, and relational debugging is able to exclude the root cause from the go runtime. Relational debugging cannot diagnose another bug because the code changed too much. However, it can tolerate small code changes between versions. Further, out of the 12 bugs, 4 only have relative root causes, which are impossible to diagnose using existing techniques. And 2 bugs can only be exposed by comparing inputs of different sizes, which makes apple-to-apple comparison impossible without applying relational debugging and identifying fine-grained reference events within the executions. Interestingly, these bugs are also among the most difficult for human developers to diagnose. We also use relational debugging to diagnose 2 open MongoDB bugs. Actually, the day after I posted the analysis for one of them, I got an email from a recruiter inviting me to work at MongoDB. So I ended up doing an internship there. Relational debugging has also attracted the attention from developers from Meta and CockroachDB and was requested by developers of the MMTK memory management toolkit. We also carried out a user study and found participants solved the bugs nearly 11 times faster when provided with relational debugging's output compared to those without it. Interestingly, we actually found that participants who looked for relative execution differences made much more progress than those who only searched for absolute execution differences. We implemented a number of optimizations in relational debugging such that it takes on average 8 minutes to run on most of the cases. And we open source relational debugging on GitLab. To conclude for this piece of work, we propose relational debugging, which efficiently narrows down to the right reference point within executions to capture the root cause of performance issues. Relational debugging returns root causes in the form of relations, which is generalizable to different performance issues. So hopefully through this presentation, I've convinced you the importance and the power of in-depth studies and of automated tools in improving system performance as software evolution becomes ever more rapid. So I'd like to conclude my talk here and take questions.
All right, thank you, Dr. Ren.